All right, so we're doing problem 6-1. All right, so we have a truck whose mass we made up, 4.0 times 10 to the third kilograms, and whose initial velocity we also made up as 40 meters per second. All right, but now, some of the stuff that was given in the problem, we know, and that is that the force of brakes, right? The braking force is going to be in that direction, right? And the magnitude of that was 3.0 times 10 to the third newtons. Is that correct? All right. And then we have a displacement of, I'll make it green, a displacement of, let's try to line that up the same. There we go. All right. So front to front, that's about how far the truck went. Go center of mass here. All right. So the displacement was 800 meters. Is that correct? 850 meters. We'll just use a D for displacement. Okay, we could use a delta X if we wanted. All right, so now the question is, what is the work done by the braking force? All right, a couple ways we can do that. Number one, if we had an initial and final velocity, we would know that the work done was equal to the change in kinetic energy, but that's our trick because that's what we're going to find out as the extension to this problem. The first part of the problem is just a simple matter of our definition of work, and that's going to be F cross D, right? The vectors, F cross D, as vectors. So that's what work is going to be equal to, work done by the brakes. The force of the brakes times the displacement over, well, that 850 meters. And looking from a strictly conceptual point of view, we have to expect that the brakes are going to slow the truck down. So if we're slowing the truck down, we're decreasing its kinetic energy, so we should end up with a negative work. All right, so we just think about that ahead of time. All right, so the work done by the brakes here is, here, let me fix this up a little bit. Instead of having that, we'll just do it like this. That's equal to F cross D. And remember, what was the definition of F cross D? That is the magnitude of F times the magnitude of D times the cosine of the angle between them, theta. All right, it's pretty easy to see. Here, we'll go with a fancy arrow here. All right, and so that's our vector for the force. So you can see that the force and the displacement, we place them tail to tail, that theta, the angle between them here, theta is equal to 180 degrees. And we should know that the cosine of 180 degrees is equal to -1. So it's pretty clear that when we multiply the magnitude of the force and the magnitude of the displacement and then multiply that by -1, we will, in fact, get a negative work. All right? So now I have to do is say the work done by the brakes is equal to the magnitude of the force, which we were given as 3.0 times 10 to the third newtons. 3.0 times 10 to the third newtons. And why don't I make that red, since that's our red vector. All right, and we're going to multiply that by our displacement vector. And the displacement vector was 850 meters. And we're multiplying that by -1, which is the cosine of 180 degrees. All right, so the -1 is easy. And then 3 times 850 is 1,700, and 850 2550 times 10 to the third is going to be 2.550 times 10 to the sixth negative. That should be the work done by the braking force. Okay, and the work, of course, whoops, terrible mistake, Mr. Fordson. We're multiplying newtons and meters, so newtons times meters is, of course, joules, which is our work unit, work of energy unit. All right, so that's the first part of the problem. That's how it's presented in the book. We have an extension here that we'll do on a different video.